surface identification and also looking at the surface distribution of composites. And the techniques used have been SIMS, SEM, and EDS. SIMS and EDS analysis of surfaces of selected unbroken and unpolished tensile specimens were done, because then they are unpolished and unbroken. That means they are the normal view. So if you take polishing and things, then you can lose some of the things, some of the bonds and things, and you see the distribution. But for these aspects, 3 samples were used along each of 1 or 2 sections of size, from 10% fly ash epoxy, 20% fly ash epoxy, and 50%, this is weight percent. So 50% means about 100 parts of resin and 100 parts of fly ash. EDS, energy dispersive spectroscopy, for fly ash, it shows, it confirms presence of silicon, oxygen, and aluminum in pure fly ash sample. This is for pure fly ash. And this is how the EDS looks like. If you scan along that, and this is what actually it shows you. This is oxygen, this is aluminum, and this is silicon. And then this is the intensity. But then also, if you take a look at it, if I go close here, we can have iron and things like the sulfur, copper, calcium, titanium. Then this is Fe, I think bit of uranium. So these kinds of things are also there. But the maximum thing is oxygen, silicon, and aluminum in these fly ash. There is no epoxy in there. Now, EDS spectra of pure epoxy, if you go there, you will see, so here there is no fly ash samples. It's pure epoxy. It shows oxygen and carbon and total absence of the elements like iron, magnesium, aluminum, silicon, and zirconium. So these are the things which you get. This is oxygen and carbon. So but the other peaks are all not present. So the other peaks which were there in the fly ash. So this is a good way to see what is there in what is there in fly ash and what is there in epoxy. What are the common things in these 2 materials? So your fly ash, EDS, epoxy EDS, and then you can go to fly ash epoxy composites. So you have this 10% epoxy, and this looks like the SEM bombardment area for 10% fly ash epoxy. And then you do the SIM study on this area, for example. If you look at SIMS, it shows within that square, it shows silicon. There is also magnesium. This results for iron is very low. Silicon is quite high. You have some magnesium. Sulfur is low. Calcium is reasonable. Potassium is reasonable. So this is quite a modern technique. And then if you go for, this is seems for 10% fly ash epoxy. What does SIM stands for? Secondary Yes, mass spectroscopy. Thank you. Yes. So this, how you can identify these particles in presence of all these things in SIMS by using SIMS. Now, EDS micrographs, if you go for 10% fly ash epoxy, so this is the, and there you can actually see, there you can see more peaks coming up here. So if you go back just for a moment in epoxy 1, there is a huge gap between this and here because there was no fly ash. But once you put fly ash, then some of the gaps are filled up. So you can see calcium, potassium, carbon. So this is what it shows. And there is epoxy contains oxygen and carbon to a great extent, and there are the other elements which are not present. So these are the kinds of things which you see. If you go for 20% fly ash epoxy, this is the SIMS bombardment area. That is where you are doing it, and then it shows SIMS results for aluminium. These are the particles which are becoming bright. They represent aluminium, and calcium are these particles which become prominent. Magnesium are here, and there you have some results for potassium. Now, a pine cone type agglomeration can be noticed, which is related to the calcium, magnesium, and potassium respectively, which all have about approximately 100 micron width. So this is the scanning electron micrograph, not polished, it's not polished, and it's not coated, just without any coating or polishing. So this is the scale bar, and this is where you can actually see that approximately, this is 50 micron, and if you go up, they're about 100 micron in this direction, so which all have approximately 100 micron width. But the most important thing notice is the 3 element agglomerations happening in the same area. So when you are actually putting fly ash in the epoxy, somehow or other it can be seen that these 3 elements, calcium, magnesium, and potassium, they show highly agglomerated, with different concentrations, whereas the K, potassium, has the highest agglomerated concentration, and magnesium has the lower ones. Magnesium is here. So magnesium you can see much lower intensity, but potassium you can see much higher intensity. So this has all the 3 elements, but the potassium comes up highest, magnesium very low, and then the calcium is in between. So this is a new kind of testing thing. So I'd suggest you consider getting a SIMS equipment in your, and we did not have SIMS equipment in our university also. But what happened, Australian Nuclear Science Technology Organization, ANSTO, they provided special fund to some universities, and it case dispersive spectroscopy was considered to be very good thing. But when we have done the SIMS, it shows that SIMS can give you much more information. The different. There's stress strain diagrams yesterday, so that we got some good mechanical properties. But the distribution of the materials are, which you cannot see in the by EDS properly, but you can see how the local distributions are. And it's at the scanning electron microscope level. So you can put SIMS through the scanning electron microscope area, but do not give any gold coating and no polishing. So this is something new. So I thought, and the very fact that even my university, University of New South Wales, did Mark-Monette Analytical Center did not have SIMS. So that shows SIMS is very expensive. But that way it also shows that some of the universities, and particularly the Nuclear Science and Technology Organization, they try to bring new facilities from other parts of the world into them. And many years ago, I had the opportunity of using some of their other facilities in looking at this ceramic matrix composites. So that's a different story. But when we approached ANSTO, and it was good that they gave us some money. $50,000 is not a lot of money. Also, people might think $50,000 is 25 lakhs of rupees, but sometimes while purchasing another things, $50,000 is often as good as 50,000 rupees. All right? So don't convert into all right. But it was good that we had this facility, and that is where SIMS was used, which gives new information. So going back there, SIMS shows for aluminum, and here you will see that aluminum accumulation, this is silicon accumulation. This is how the equipment shows, and this is the thing which you have typed there, but this is what it comes up with in this result. This is for oxygen, SIMS result for oxygen, SIMS result for manganese. And in all areas, we kept the scale about the same so that you can see the concentration and the distribution of these materials. So some of these materials, manganese, aluminum, they seem to be quite well distributed. Silicon is very low and there is distributed only, there's a huge area where there is no silicon. And here you have some oxygen, but the distance between the oxygen molecules of the atoms is larger than some of these. So that's why I was saying, do any of you have SIMS equipment in your laboratory? It may be worthwhile going for that. SIMS, okay? So that can give you really new information. And when you see that, then all these affect the properties, because they actually interact with the epoxy. But this kind of thing you do not see in the EDS. All right? So SIMS can be much useful, valuable information. Now, EDS micrography for 20% fly ash. And here you can see only carbon and oxygen can be found. No manganese, Fe, calcium, and sulfur. So this is the EDS. And if you go for the SIMS, now we are, okay. This was for 20%, and you can see all things in the SIMS. But when you do the EDS for 20%, you do not see any manganese or Fe or A. So that's what shows that SIMS can give you much more information. Now going to the 50% fly ash, again here, this is the area, a similar square area you are looking at, and then you go for SIMS, and it shows that SIMS has less presence in sin for magnesium and enriched evidence of aluminum. So this is aluminum, calcium, potassium, and silicon in these clouds, along with some bright particles of agglomeration. Where you have light particles means there are some things all have come together. So this is also interesting observation. Uniform distribution in the matrix for iron and sulfur. So these are the iron particles, and this is the sulfur particles. And you can see there are more iron with closer distribution, whereas there is less sulfur with more distance between them here. But then once you do that, you can go back to use some of the scanning from microscope like program, so you can work out the distance between the sulfur particles. Okay, like so SEM, SIMS, and then also use a SEM particle-to-particle distance programs. So things can be much more informative. Now, going back to the EDS for 50% fly ash composites, there is this silicon as well as carbon and oxygen can be found. So this is where you can see in this composite. And this is the main difference between this composite and the 10% epoxy and 20% epoxy system. So somehow or other, when these composites are made, now the fly ash has the same composition. You are using the same fly ash. But when it's going into the matrix, somehow or other the distribution and the agglomeration or concentration, that changes. That's where the chemistry and movement of the particles, they all are involved. So again, here you can see this white dots, they are the fly ash particles. But some of the particles may not have been inside, but they may be under the surface. But this is where you still have a big gap, but this thing shows calcium and oxygen. Now, I'm not an expert in SIMS, and very few people have expertise in SIMS, but there are always new things do come up. And Dr. Sheila Devasahayam, she is from Chennai, but she has gone there for many years. She did her PhD both in Chennai. She used to use National Meteorological Laboratory. You are familiar with that, NML? NML Jamshedpur, she used to work there, NML. And Sheila Devasahayam. Sheila, Sheila. I'll write her name. I have quite a few papers with her, and she is very active. Dr. Sheila Devasahayam. Sheila, Sheila, and Devasahayam. She used to work in NML, but she has gone there. But she is at the moment in a university called Macquarie University in New South Wales. But if you contact her and things, you might interact with her. And she has a lot of contacts in India also. But it was her initiative that we got access to SIMS. She was the primary person who actually did that, but then I was a secondary person. Sometimes having a second person helps when you apply for funds and things. You put your name, but also it is good to have two or three more people, because they go through all the experience and background of the team, and that helps it out. Okay. If if you put coating, then the coating comes up. So it's better not to give any polishing, not any. During exposure, it shows what it takes a scan of the area where you are doing. It's not burning. It's not infrared, it is the SIMS. So I think I understand that the way you do that, it's like that it shows that's the entire SEM picture, and then you focus on it. You say the SIMS go on there, the SIMS just goes on there. It does not burn or anything. It just highlights that area. It says that this is the area. That may be the type of there. Find it out and let me know. Okay? I would love to say that I know 100% in everything. I don't know 100% of everything. Okay? But if no, gold coating is not done. No, not for the SIMS. Yes. Okay, that's all right. But we are talking about the SIMS give you all this information. Okay. But you can contact her, and then you can, because sometimes she's such a, people from Tamil Nadu, they are very active. Anyone from Tamil Nadu? Oh, okay, all right. They are very active, highly interactive, okay? They won't let you go. And till they get the answer. Sometimes when I organize conferences in 2012, I organized the 6th International Composites Conference, and I did at Monash University. So I said to Dr. Sheila, you come and make your presentation, all those things. And there was a very big audience, about 250 and 300. So she spent about 1 hour in presenting her thing. So that's how you spread the information and the knowledge. But material science and engineering is such a thing that I would love to say that I know 100% of it, but that will be a big lie. I don't want to say that lie. Because knowledge keeps on increasing. What you know today, the same thing after 2 or 3 years, new things have come, you get new information. All right? But the old information also stays there, and you keep on adding more new information. And the same thing comes from the audiences like you people. All right? So that's why I'd like to get your views, because you have different specialization. If you could say something so I can learn from you. All right? But you say in EDS it is gold coating is done, is it? Have you got EDS equipment? Okay. Huh? Okay. So EDS gives gold coating. Everyone, okay, but the okay. So you have the gold coating on the epoxy and the particles. But did you put a reinforcement like fly ash or something else, and then you also give gold coating? Does the gold come out in the why doesn't it come out? Why doesn't it get money? Okay, all right. Now the corresponding SA microscopy of the surface. Now if you take a look at the fracture surfaces and going to higher magnification, the 10% fly ash epoxy shows some micro cracks and crack profiles as well, a small one. The surface of 50% fly ash showing that the particles well bonded to the epoxy and also evenly distributed. So here you can see that there is no cracks here in the 50% fly ash. So that is a good thing. If you have small cracks there, then when you're doing particularly under tensile testing, the cracks can expand. But there are other elements like compression and shears. The cracks may not be that much of a problem. Okay. This is the PhD student. She's about to finish. Her name is Ms. Shahad Ibrahim. And she did this shear ball milling of fly ash. So this is, you put the things there and do ball mill. That means they put spherical particles. So these are the spherical balls, like maybe ceramic balls. And these are the fly ash particles, small particles. So it's grinding. So that way you generate smaller fly ash particles. So this is the fly ash sample prior to ball milling. Balling, I think every laboratories can have ball milling, isn't it? You have, and then after 10 hours of ball milling, this is the fly ash samples, how the same one looks like. Now, then you have to do the analysis of the particle size, and we have some facilities in the civil engineering department, and then they helped us working out the particle size distribution. So 0 hours ball milling, the particle size starts from about 1 micron, and the maximum goes to about 100 microns. And when you go to, this is on the logarithmic scale, and when you do up 10 hours, so you get particles, I think about 0.5 micron here, and the largest you go to about 10 to 20 micron size. So if you have large particle size, you can break it down and you can make it smaller. And also a small amount you can get below 1 micron, so about 500 nanometers or something like that. So particle size, D10, D50, D90, size fraction. So 0 hours, particle size, you have 1.905, like that. And here, after 10 hours, the size goes up like that. You have. So this is 1905, and this is 955. 8.7, this is 4.65, and here from 19 or 20. This is the fraction. What is the 10% fraction? What is the 50% fraction? What is the 90% fraction? So this is not the straightforward particle size. This is the fraction of the materials. So after 10 hours, you can see that everything comes down by a factor of 2. So that means the surface area comes down or goes up, not comes down, goes by a factor of about 4. All right? So that gives you more bonding areas. XRD, X-ray diffraction analysis. XRD for raw fly ash goes like that. Malite, this is glass, because glass is not a crystalline material, it's amorphous, but these are crystalline materials. So you have malite, quartz, more peaks of malite, quartz, malite. So mostly malite and some quartz. Then XRD for 10 hours dry ball mill fly ash, you get the peaks, actually peak intensity comes down. Peak intensity comes down. So even for the malite and quartz, all the peak intensities come down. And you still have quartz, but the intensity comes down by a factor of 2. Like you have 180, and it comes to about 95. So things like that. So again, comes down by a factor of 2. So this is quite interesting. But you still have the quartz, and so the peaks are the same, but the peak height comes down. So here this is a malite 4,000 intensity, and here this hemalite comes to about 2,000. So factor of 2, and this is the 2 theta. Benefits of fly ash addition in epoxy. A 60% increase in yield strength was observed with 10% fly ash, which you remember in the slide showing yesterday. Then chemical bond studies without and with fly ash using FTR spectroscopy confirmed that fly ash chemically interacted with epoxy, which we have seen before, which is a novel information indicating beta curing reaction. And that was the FTIR which we showed yesterday. And also today, SIMS for selective fly ash epoxy composites proved good and even distribution for elements of aluminum, Fe, silicon, but clustering of magnesium. So the flames showed that if you have magnesium, magnesium ions or magnesium atoms, they show clustering. But the other things, aluminum, iron, silicon, calcium, sulfur, they have even distribution. So that will again affect the properties of the material. Sometimes it can make it more stronger in some areas, sometimes they can make it. Also, mechanical properties are good. Remember, yesterday we showed that for the 40%, fly ash, the strength went down, but the ductility went up. So it could be that when you have 40%, so this is an explanation which people cannot get from the normal tensile testing. How come in some cases strength goes up and some cases strength comes down? So this could be giving some answers that if you have certain about type of distribution, there may be even distribution, but if you have certain types of distribution, there may be clustering. And if you have clustering, means there may be more particles bonded there, and that can initiate some cracks. If you have more clustering, because they become more combination of these ceramic particles, so it's much more brittle. So the cracks may start there, and once the crack starts, then the stress comes down. All right? So it is worthwhile using these things, showing that what kind of, so even before you do testing, if you do the SIMS and things, and then you can give a prediction that those which have clustering, that might cause some lowering of strength. All right? So that is what it can show. And the conventional ball milling reduces the particle size of fly ash by 50%. That means by a factor of 2, and inducing a 4 times increase in the surface area. Which, yes? Can you speak louder? Everyone can hear. Why intensity of each peak is coming down? Maybe what it may be that it is intensity. I think it depends on the intensity. Intensity is related to the concentration of the particles, I think. And that's what they. But the same studies are being all studied under the same voltage. The details are given in published journal paper. So if you write to me, I can send you the journal paper. Okay, but when we are doing this EDS and SIMS and things like that, it's always under the same voltage. Do not change any of those external parameters. Okay. So if you use ball milling, then you can reduce the particle size of fly ash by a factor of 2, and that increases the surface area by a factor of 4, and that means it makes the bonding capability more. So you have more surface area, so more stronger particle size, and which can be a good achievement in future studies. So the conclusion of this one is adhesive fly ash waste was found very attractive as an additive in epoxy resin by up to 50%, reducing the cost of the used matrix by about 50% and achieving a result of superior properties. So that means if you are using less amount of epoxy, so then you can save some money. But more importantly, this shows how ball milling can help. Now, in some cases, if you use ball milling instead of 10 hours, if you go for 20, 30, 40 hours, you never know, it might bring down to smaller particle size. Maybe to about, instead of 500 nanometers, it might bring down to maybe 100, 200 nanometers. So, yes, if you can do that. If you can do that. But this was done in a now again, high energy ball milling. These are ball milling used by ceramic people. Okay, these equipment are used by ceramic people. So you don't go for very high ball milling, but they are standards, and in the publication it will be given there. And this is where I took the support of Dr. Owen's standard. He's an Australian boy. He's an Australian guy, and he is an expert of ball milling. So it's always good to take the permission and use him and the technician, so that we use the standard method. Okay. So I always insist that some experts actually do help the researchers. All right, and they do so. Yes? No, we don't do any heat treatment. We try to use adhesive fly ash every time. Yes, fly ash factory in Brisbane, and in fact, they provided all those fly ash, and also they provided as a fund. And not only that, there are two people. One is the administrative, and another is the engineering. So whenever we publish papers, so we took consent from them, and we acknowledge that company because they gave us funding, and they also came and also my students went there and they had training there. So it's good that when they come back, they can see the things and they can even suggest how you can improve. And the people came from the fly ash company. They used to be very surprised, and I said yes. So they are students today, but after 3 years, they will have their doctorates, and so we want them to have all the information while they are this research scholar and things like that. Okay, and that's why I work, and I also promote my students in the university magazines rather than putting me there. I said such and such, put his photograph, and they highlight it. Okay, something like that. This is not yet the whitening. Whitening we talked yesterday. No, it's not. You can use it anywhere. It shows that the color of fly ash changes to 96%, 95% whiteness of. Then you can use it anywhere because you need any plastic. You can polyethylene, polypropylene. Yes, it attractive means that from visibility point of view and light reflecting point of view. And as I said, that's what I thought. And then when the Director General of CPET, when he saw that it even improves the impact fracture toughness, notched impact fracture, sharp impact fracture of polypropylene by 50%, he almost jumped up. So it's better for people who are using it, them to see and good to jump up rather than me and my students jumping up. We don't jump up. We say that show your results to the people. And that fly ash industry, they were so happy and spirited. Okay? So that's how the thing is. Bring them, because then from them we can get to know which aspect is very, very contributing.
What I collected is around 40 microns. After heat treatments, the size is decreased to around 4 to 5 microns.
Size of what?
Size of the particle, fly ash particle, from 40 to 4 microns.
I have to see your results and I have to see the particles. Because what is it that will reduce the size of the particle? What does the heat treatment do? What does the heat treatment do?
Treatment it is around 700 degrees. I think it costs 6,000.
But how does it reduce the particle of the
Around 3%.
LOI?
Unburned carbon is totally nil.
Okay. But why do the particle size go back by 40 to 4 means about 10 times, 1,000%? Why the,
And the color also seems too white, almost white.
yeah, that is one way of doing it. But if the particle size comes down, that is good. But just double check about the particle size. All right? Okay. But that's good. Well done. Okay, so we'll go to the next lecture. So let's take 5 minutes break. Are they serving tea outside 3 o'clock? Holy tea?